So in part 2, we're going to start doing the actual application, the full-blown problems, as they call them. Again, please don't panic. Just remember that these are straightforward writing, and as you read the sentences from left to right, you do need to define your variables so you understand, and I understand, and everybody else understands what each letter stands for. So in example 2, it says the period of a pendulum is the time required for one oscillation. So a pendulum would be like the pendulum on a clock going back and forth, or child on a swing going back and forth would be the same kind of idea. So then it goes on to tell us the period of a simple pendulum in seconds varies directly with the square root of its length. So that's the sentence I need to be able to write my equation, but I need some variables. So first of all, I need the period of a simple pendulum. So for example 2, we're going to come in and let P stand for the period. You can use any letter you want. I try to be descriptive. In physics, they actually use a T because it's a time. We'll use P because it makes more sense for us. So it tells me that the period varies directly with the square root of its length. So in other words, how far it takes to go back and forth, how long it takes to go back and forth, depends on the length of the string or the swing or the pendulum. So I'm going to use an L, and I tend to use a script L or a cursive L because otherwise it looks like a 1. So this will be the length. So I've defined my variables. Now I can come in and take that sentence to write my equation. So it's the period varies directly. So P equals K. And because it says directly, we know that whatever is following that is right next to K, the square root of its length. So then I have the square root of L. And there's our beginning equation. So we wrote the equation after we defined the variables. Next, we're going to use the first set of numbers to figure out what K is. So a period is a pendulum is 32 centimeters. Well, that's a length. So over here, I'm going to have the square root of 32, where the L is. Completes one oscillation in 6.28 seconds. So you'll notice those decimals rearing their head. Yeah, in the real world, numbers don't come out nicely. So we now need to solve this for K. So K is going to be equal whatever 6.28 divided by the square root of 32 is. And if you do that on your calculator, you're going to get K is equal to 1.11. Now I'm going to use 2 or 3 decimals depending on the problem. Don't use less than 2 decimals or you won't get the book's answer, or the answer is correct on the online homework. So now it's asking us to write an equation that relates the quantity. So we now know that the period, no matter what length of pendulum we have, is that 1.11, that's our K, times the square root of L. And there's our first problem. So we wrote our equation of variation. So again, write those equations as you read those sentences. Let's try example 2. I'm sorry, example 3. That was example 2. So example 3 tells us the rate of vibration of a string under constant tension varies inversely with the length of the string. And you read that and say, what the heck is the rate of vibration of a string? Think of a guitar string, right? It's under tension because it's tied on both ends. You pluck it, it vibrates back and forth. That's what they're talking about. So the rate of vibration of a string under constant tension varies inversely with the length of the string. So I need some letters again. This time I'm going to be a little more descriptive. I'm going to use V for the rate of vibration. Rate of vibration. Again, I'm going to come in and use L for length of the string. So this will be length of the string. The same thing is true for a wire in a piano. It's also under tension. Okay, let's write our equation. So the rate of vibration, I call that V, equals K. And then it says inversely. So I know that whatever follows the word inversely goes in the denominator, the length of the string. So V is equal to K divided by L. If a string is 48 inches long and vibrates 256 times per second, comma. So that's the next phrase or part of the sentence. They've given me both L and V, so now I can go find K. So if the string is 48 inches long, so K over 48, and that's going to be equal to 256. So we're simply going to solve for K by multiplying both sides by 48. And if you do that, you get a really large number. It comes out to be 12,288. And again, it's unitless as far as we're concerned. It just works best for our class. So now we have an equation. So V is equal to 12,288 all over L. And in the previous examples, that's where we stopped. This one asks us an additional question and then goes on to say, what is the length of a string that vibrates 576 times per second? So now they're giving me a second set of numbers to come in and find the unknown or to answer the actual question. So in this case, they're telling us the rate of vibration is 576. We want to know how long of a string we're going to need to hit that pitch or note. So to do this guy, we're going to multiply both sides by L. That's going to clear the fraction. So that'll give me 576L is equal to 12,288. And then we'll divide by 576. So L comes out to be 21.33 inches. So if I want to hit 576 times per second, then I need a length of string that's 21.33 inches. So for the first time, they've given me a set of numbers and then asked an additional question with another set of numbers. I think these are kind of fun as far as word problems go. As long as you know those three main types of variations, they're fairly straightforward. There's not a lot of ucky stuff in them. Example 4 says, the collision impact of an automobile varies jointly as its mass and the square of its speed. Suppose a 2,000-pound car traveling at 55 miles an hour has a collision impact of 6.1. What's the collision impact of the same car at 65 miles an hour? Okay, so we need a couple of variables. The collision impact of a car. So let's just use C. So C is going to represent the collision impact. And it varies jointly as the mass. So we use M for mass. And normally I would use S for speed, but my S's look so much like my 5s. I'm going to go the physics route and call it V. So that's going to be our speed, which is our velocity. So that's why I can go with V. It's a velocity. Okay, now that we have our variables defined, we can come in and write the equation. So we're going to use the first sentence and write it as we read it. So the collision impact, that's C. Varies is our verb. So there's the equal sign immediately put in your K. Jointly, which means whatever follows it needs to be multiplied together. The mass and the square of the speed. So we have C is equal to K times M times B squared. Suppose a 2,000-pound car, well, 2,000 pounds is a mass. So we're going to put the 2,000 in for the mass. Traveling at 55 miles an hour, so we'll put 55 in for our speed, we need to square that, has a collision impact of 6.1. And I'm sure that this is something that the insurance people know about. We now need to solve for K. So we're just going to divide everything out. So I'm going to let the calculator do the grunt of the work. So we're going to take 6.1, I'm going to divide it by 2,000 times 55 squared. Whatever you do, make sure you put instead of parentheses around the entire denominator, otherwise you'll get the wrong answer. So again, I have 6.1. We're dividing it by the quantity, 2,000 times the 55 squared. If you do that, I ended up with a really teeny tiny little K. I ended up with 1.008 times 10 to the negative 6. On the calculator, it shows up as an E and then negative 6. It simply means that the decimal place has been moved over 6 places. So this is really 0.1, 2, 3, 4, 5 zeros, then the 1. And there's the 6 places that we've been moved over, 0, 0, 8. So pretty tiny for whatever K is our constant. So we now have an equation. So we now know that C is equal to, and I'm going to pick up this one because I think it's easier for you guys to type into your calculator, MB squared. If you know how to use scientific notation, go ahead and use this one. It's not a big deal. Then goes on and says, what is the collision impact of the same car at 65 miles an hour? So in other words, if I speed up by 65 miles an hour, how does that change that C or collision impact? Well, we're going to pick up the same K. 008. Our mass is still the same 2,000-pound car, but now our velocity is 65 miles an hour, which we're going to square. So again, we'll number crunch that through, and I ended up with 8.5 as my collision impact. Now, the original collision impact didn't have a unit on it, so I don't know what unit to put on this thing, so we're going to leave it unitless just like they did.